actually the first time. All right, show recording, great. Okay, so hello again. Section 3.2 is basically a bunch of characteristics of what we call the graph of a real valued function. Right? And so we've seen graphs in the previous section, but they weren't linked to an expression, an algebraic expression, right? A lot of what we're going to end up doing is taking an algebraic expression, defining a function from it, and then learning how to graph it, right? So the examples we looked at weren't like that. But before we even get there, we need to talk about some various characteristics that functions can possess so that we can actually use those in interpreting certain things in context for those functions. So first things first, what is a graph of a function? Well, it's simply a collection of ordered pairs, right? You take every x, and to every x value, you associate a single y value. If you look at that as an ordered pair, the collection of all the ordered pairs can form a curve in the plane. And so that's what I'm calling the graph of the function. All right, so when you're given an algebraic expression, so if this were x squared plus 5, let's say, when you're given such an expression, then what you know is that if I gave you a particular x value and you computed the y, the fact that x comma f of x, the fact that x, when you plug it in and get the y value, satisfies that equation means that the corresponding point x comma f of x is on the graph, right? So for instance, if it was y equals x squared, if I put 2 in for x, I get 4 for y. That means f of 2 is equal to 4. But that also means that 2 comma 4 is a point on the graph of y equals x squared, right? So there's that back and forth correspondence between the algebra and the geometry. All right, so if we have a graph, first off, how do I know it's a function, right? So not everything is going to be a graph of a function, because we have that subtlety that every input has to map to exactly one output, not many, exactly one. And so for instance, a circle, right, would not be the graph of a function, because an input here, right, so the x coordinate that corresponds to the point on the x-axis right here has 2 outputs, has one there and one there. Because remember, the outputs when put together with that x give you an ordered pair on the curve. And so if there are more than one point on that vertical line that's on the curve, that means that that value of x has more than one output. It cannot be a function, right? So it's something called the vertical line test, right? Just to give it a name. If any vertical line hits the graph in more than one spot, that graph does not define a function, right? So this guy here is fine. Give me any vertical line you want throughout. It's going to hit that graph in more than one, in exactly one spot, and that's not a function. All right, so let's look at just some examples. We looked at this example algebraically before, and it might have caused heartburn because you didn't know where to put the x if it was always equal to 5, right? So let's start with that just to get a picture of what that looks like. First off, that you always want to have the domain up front, right? Because you want to know where in the xy plane you're actually going to plot the function's graph. And so here we want to ask, is there any number that we have to exclude from the domain? Is there anything that makes this undefined? And the answer is no, right? It's always defined. It's always 5. So if you give me any number, -3, -1, 0, 1, 4, any other number, million, let's say, the output's always 5. Right, and so remember the points that you get from this table, namely the ordered pair -3, 5, -1, 5, 0, 5, so on and so forth. Those are all points on this graph. And so if I were to plot those points, the one thing you want to notice is that they're always at a y value of 5. And so what you're going to get here is this horizontal line as the graph. Right? That is a function. Don't confuse this with the vertical line test. That's a function because every vertical line hits that graph in exactly one spot. Okay. All right. How about y equals x squared? So what would this look like? Well, let's plug in some values. right? So if I put in -2, -1, 0, 1, and 2, let's say, the outputs I'm going to if you know nothing else with functions, you want to form a table of some standard values just to get a feel for what the graph looks like. And so if I plug in -2 for x, remember I'm squaring the -2, and so you get 4 back. And if I plug in -1, you're squaring the -1, so you get 1. And then same way with 0, 1, and 4. All right, and so if you were to plot those values like I did here, right, if you kept plotting values in between these in between 1 and 2, in between 0 and 1, so on and so forth, you'll see that there is a general U shape that develops, right? And the one thing that becomes evident is that if you square a negative, the negative goes away, right? And so -2 and 2, they were both the same distance from the origin. They have exactly the same y value, right? And so you have a certain type of symmetry, we should say, about the y-axis. If you go 5 units to the right on this side or 5 units to the left on this side, those points are going to have the same y value. All right, so we call this graph a parabola, right? Any quadratic, any x squared sort of function is going to look like this. It might not appear there. It might be moved over here. It might be tighter, or it might be wider. It might be flipped over, but it will always have some sort of U shape attached to it. All right, so now let's talk about some attributes. Intercepts, right? So the graphs of some functions cross the x-axis, some cross the y-axis, some cross both, some cross neither, right? So it just depends on what the nature of the graph is. But a point at which it crosses the x-axis is called an x-intercept. And on the x-axis, if any point on this x-axis, the y value is equal to 0, right? And so the point x comma 0 would be the form of an x-intercept, right? And same way on a y-intercept would have to have a form of 0y, because on the y-axis, the x is 0. All right, and so that tells you a way to find these. If you have an algebraic expression for a function, to find the x-intercepts, you set y equal to 0 and solve for x. If you want to find the y-intercept, you plug 0 in for x and you get the y value out. Keep in mind that you can only have one y-intercept, because if you had any more, the graph would not pass the vertical line test, right? The y-axis itself is a vertical line, and so if it crosses the function's graph more than once, that graph would not pass the vertical line test. But you could have any number of x-intercepts, and so I just give you some examples here. This line has one x-intercept, right, namely 4, 0, and one y-intercept. This graph here has a y-intercept, namely 0, 1, but it has no x-intercepts. It's always above the x-axis. This one here has neither, right, as you can see. And this one does have a y-intercept at the origin and crosses the x-axis at every integer, right? So you have infinitely many x-intercepts for this type of function. All right, positive versus negative, right? So if I'm talking about a graph, the graph will be positive when its y values are positive, right? So pictorially, the graph lies above the x-axis if the function's positive there, and we'll call it negative on an interval if the graph of the function's below the x-axis, right? So here's 2 examples of that. Certainly, a graph can oscillate from above to below or vice versa. So then what you want to do is specify each interval on which it's positive and each interval on which it's negative separately. All right, so I give some examples here. Whenever I use this symbol, that means the empty set, which means there are no x values for which the function's negative. Okay, okay, increasing, decreasing, and constant. So always here, when you're characterizing a graph as being increasing or decreasing, you are assumed that you're moving from left to right in the domain, right? So for example here, you always start with the leftmost x to the rightmost. And what we'll say is the function is increasing on this interval because the y values are increasing as a set of numbers. Or if you want to think of it geometrically, the graph is literally rising from left to right. Likewise, we'll call this function decreasing on this interval because as you move from A to B, so from left to right in the domain, the function is falling, or what that means is the y values are getting smaller. And then finally, we'll call a function constant on an interval if the y values don't change. They hold literally constant at the same value. All right? Notice that we always report the increasing, decreasing, and constant nature on the interval in the domain for which it's true. All right, so you don't list this as point to point, literally. You list it as an interval of x values. So for instance, here, let's look at this graph. That's a parabola. To the left of x equals 1, the graph is falling, so it's decreasing. So what we'll say is f is decreasing from minus infinity to 1. Same way here, to the right of 1, we'll say the function's increasing, right? So we'll say it's increasing on 1 to infinity, and it's never constant, and so we'll say it's constant on the empty set. Okay. Similarly here, notice that between -2 and 2, the function's constant, and so I have this set. And then to the left of -2, it's going up. To the right of +2, it's going up. So the function's increasing for all x values in these intervals. One thing you'll also notice, and it's a subtlety, it's not really all that critical, but you notice I'm always using open intervals here. You typically don't include the x values where it changes from one to the other. That's just convention. It doesn't mean it's wrong if you do. It's just convention to list them as open intervals. All right, high and low points. So these are kind of intuitive. A high point is simply a value where the function kind of maxes out, but close by. It doesn't have to max out on the whole domain. It just has to max out for x values nearby, right? So for instance here, the value at this peak would be a high point because close by, the y values are all smaller than it. This guy here at this low point, at this vertex, that's a low point because for x values close by, all the other y values are above it. Okay, so think of them as local max and min. Local simply means that I'm looking at only x values close by, not the entire domain. That would be global, right? We're not looking at those at the moment. I'll let you read through those. Those are just some more pictures of illustrating all those. Okay. In terms of symmetry, I spoke intuitively about symmetry about the y-axis when we talked about x squared. Let's talk a little bit more formally about it. We'll say a function's graph is even, or what that means is symmetric about the y-axis. If, give me any point to the right of the y-axis, if I go the same distance on the left of the y-axis, I have the same y value. And so by the same distance, the way you get points like that is by taking their negatives, right? So what we can say is that negative x and x both have the same y value. But remember, the y value of those points is equivalent to the functional value there, right? And so an algebraic way of codifying that would be to say that f of x is equal to f of negative x, right? That means the same thing, okay? The reason we call that even, by the way, just kind of a note, is that the prototypical even function is y equals x squared, right? It's an even exponent, and so we have an even function. Not all quadratics are even, right? The symmetry is about the y-axis, not just about any vertical line. So be careful, but historically that's why that came up. The prototypical example was y equals x squared. All right, now you could have other type of symmetry called symmetry about the origin, and we call this odd, all right? And so what it means is that if you take any point on the graph to the right of the y-axis, let's say here, if you were to fold that along over the y-axis and then over the x, you get that point. All right, and so what does that mean? If I go a distance to the right of the y-axis and have a point, the corresponding point that you obtain by going the same distance to the left of the x-axis is the one with the opposite signed y value, right? And so notice here that at x, y, I'm in the first quadrant. the corresponding point here is at negative x, negative y, which means I went the same distance on to the left of the y-axis and the same distance below the x-axis that I went up to get that guy. So for instance, if I had the point 1, 3 on the graph and the graph was odd, then the point -1, -3 would be also on the graph. Right. Now, as you might guess, the reason why we call this odd historically is that the prototypical function that is odd or possesses this type of behavior is in fact y equals x cubed. Right, and you can check that out by just forming a table of values and showing every time, give me any x you want, if I take the negative of that x, the way you get the y value is by negating the y value that you got originally for that x. All right. This thing, for end behavior, this will be more important when we talk about polynomials and asymptotes for exponentials and logs. But I pointed out now I wanted to gather all of these properties together just so that we can make reference to them in terms of a toolbox. All right, so what end behavior means is what happens to a graph for very, very large x values in either direction. Right, so for instance here, if I affix an arrowhead like that to the end of a graph, and that's it, right, it's assumed that as x gets large, the functional value goes up indefinitely. So it extends to infinity, we say. So what I would write to indicate that sort of behavior is that f of x goes to, that's how you read an arrow, f of x goes to infinity as x goes to infinity. Okay. Same way here, this end behavior would be as x goes to infinity, f of x goes to minus infinity, right? It's dipping down to the negative values. Sometimes there's a line to which the graph gets close as x gets big, right? And so here, as x goes more and more to the right, the functional values seem to be getting closer to the function's graph rather seems to get closer to this line, which means the functional values f of x approach L, or they go to L, right? So in this case, we have something called a horizontal asymptote. That'll come up later on when we talk about rational functions and their graphs and whatnot. All right, and then here for this tortograph, it just continues on up and down in the same pattern. The function doesn't really approach any number as x gets big, nor does it go to plus or minus infinity. And so we say f is periodic. It oscillates with a regular pattern. And so those sorts of functions will come up when we talk about trig later on. Okay, so those are the main characteristics of functions that come in handy in applications. Let's look at a couple of these applied problems just to interpret how you use them. All right, so for example 3, suppose that your body temperature for a 24-hour period during which you have a virus is given by this graph. Okay, so here the T is in hours and the y-axis is in temperature in degrees. All right, and we're calling T equals 5 a.m. on Monday. Okay, and then we're going to go for the whole 24 hours, so that's a full day's worth of body temperatures. And what we want to know is during what time frame was the temperature increasing, right? So for what times on the horizontal axis is the temperature curve going up, all right? So certainly I'll start at 0. It looks like it's going up all the way until I get to 10 hours, which would be T equals 10 more corresponds to 2 p.m., right? Because we started at 5 a.m. and we've gone 10 hours. All right, and so here, what we would say is that the temperature is increasing on the interval from 0 to 10. Remember, you always indicate the values on the horizontal axis that correspond to where the function is increasing or decreasing. All right. Part 2 is asks what was the maximum temperature. Well, here we're looking for the high point, right? And the high point occurs at this peak here. The maximum is the y value. It's not the actual x value, it's the y value, because the y value itself is temperature, and that's what we're asking here. What's the max temperature? And so the max temperature is 102.2 degrees. Remember, units are important here. Okay. And then the third question is, what does the y-intercept of this graph mean in context? Remember, the y-intercept is the intersection of the graph with the y-axis. But remember, on the y-axis, t equals 0 corresponded to 5 a.m. on Monday. And so what this point means, remember this point is 0, 99. It is your body temperature in degrees at 5 a.m. That's what that means in context. All right, I will let you do your turn one. Right, I'll let you do that, pause it, and then you can check yourself afterward. It's similar in nature to the other one. So give that a go. All right, and take a look here. Make sure you got that under control. And then the last example is fairly similar as well. So I'm gonna let you read that on your own. Go ahead and try these problems. For the most part, they're not that bad. A lot of contextual problems. Number 9 typically gives people heartburn. You might have a little bit of heartburn with 8 as well. Sorry for the poor graph there, but you kind of get the idea. Anyway, so piddle around with this, kind of see, get familiar with the terminology and whatnot, and let me know how it goes. All right, take it easy. Bye.